So I've only discussed silicon so far, and it's the most used semiconducting material, but it's not the only semiconducting material. The reason why silicon is semiconducting is because of the way that it covalently bonds. And the reason why is because it has these 4 electrons in its outer shell. So if you go back to the periodic table, if you look in group 4 of the periodic table, well, actually all of those elements have 4 electrons in their outer shell. So they also bond in the same way. So if you look down that row, you can see you've got carbon, and actually diamond is a semiconducting material, and you've got germanium, and germanium is also heavily used as a semiconducting material because they bond in the same way. So if you were to look at the structure, it would look exactly the same. Here's the structure of silicon, and because we're only interested in those outer electrons and what they're doing, germanium would look exactly the same, for instance. If you go back to the periodic table again, you might notice, well, actually there's something else that's quite clever that you can do, and that's if you took a mixture of elements from the group 5 and group 3 of the periodic table, well, they would also covalently bond in the same way as long as they're in a 50-50 proportion, because together they would be able to have the same sharing of electrons. So for instance, gallium arsenide would look in exactly the same configuration as silicon or germanium, because you've got 3 outer electrons from one and 5 of the other, and they share those. Something else that you can do, because I mentioned that the band gap of semiconductors is dependent on the type of material you're using. So what you want to do, if you want to fabricate a material where you can change the band gap for your own applications, you can use a different mixture of elements to suit your needs. So if you take elements from group 3 and group 5 of the periodic table and mix them, they're called 3-5 semiconductors. What you can do is take a different mixture of 2 elements from group 5, for instance. It's a little bit complicated, but I'll zoom in and let you have a look. So for instance, if you look at, I showed you gallium arsenide, you need that in a 50-50 combination in order to get the correct bonding, and that would have a particular band gap. However, if you mixed the gallium with another element in the periodic table in group 3, which has a different band gap, then you can adjust the band gap for whatever your applications are. So you can exchange one group 3 element for another. So an example is gallium indium arsenide, where you've got 50% arsenide, but actually you've got a mixture between the gallium and indium, and this is denoted as shown on the slide here. In all of these semiconductors that I've discussed so far, at T equals 0, so absolute 0, you have no electrons in the conduction band and the valence band is completely full. And as you raise temperature or add energy to the system, a small fraction of electrons becomes thermally emitted into the conduction band, as long as that energy is bigger than the band gap energy, bigger than or equal to the band gap energy that you see here. So all of these semiconductors, whether they're made of one single element or whether they're made of a compound, so a compound, so 3-5 semiconductors are known as compound semiconductors, they all act in this way, that in order to get conduction, you need to get electrons from the valence band into the conduction band. And these types of semiconductors, which we've described so far, are also known as intrinsic semiconductors. So there are a lot of new terms in this week's material, and you need to sort of get a grip on all of these terms. In intrinsic semiconductors, for every electron that is thermally excited into the conduction band, it leaves behind one single hole in the valence band. So they're equal to each other. The number of free electrons that conduct in the conduction band is equal to the number of holes, positive holes, in the valence band. So you can write this in terms of N equals P, and N is the number of electrons in the conduction band per unit volume. That's just the standard way of giving it. And P is the number of holes in the valence band per unit volume. And that's in an intrinsic semiconductor. And we can also say that's equal to Ni, which is known as the intrinsic carrier concentration. Now, you know that this is temperature dependent, so I've given the equation here where the number of electrons in the conduction band is directly proportional to the exponential of minus the band gap energy, Eg, divided by 2 kBT, where kB is Boltzmann's constant and T is the temperature in Kelvin. Now, conductivity gives you an idea of how conductive the material is. So that is directly proportional to the number of charge carriers that you have. So conductivity, and the symbol is sigma, is proportional to n, which is also proportional to this exponential term. So if you were to plot this on a graph of conductivity versus temperature, you see that as the temperature increases, you get more and more charge carriers, you get more and more electron hole pairs, which are involved in the conduction process. So that has an exponential shape. Well, what about metals? Well, hopefully you know, see here you've got your free electrons and you've got your atoms. They have a bit of thermal energy, so they're vibrating. If I start my potential difference across the material, you have current flow through the metal. And now if I increase temperature, you can see that these lattice vibrations, the atomic vibrations, increase and they start to impede the flow of electrons. So the higher the temperature is, the greater the resistance to the flow of electric current. So you know that when a conductor gets warmer and warmer, a metallic conductor gets warmer and warmer, its resistance reduces linearly because of these lattice vibrations. And a semiconductor is the other way, right? The warmer and warmer it gets, the more energy those electrons get to break free of their bonds, they enter the conduction band and they can conduct. However, their conductivity is still a lot lower than a normal conductor. In fact, I can give you some numbers. So gallium arsenide, one of the 3,5 materials, at room temperature, the number of free electrons in 1 cubic centimeter is only 1 million. Okay, these numbers sound like a lot, right? And silicon has 10 billion. But if you compare that to an average metal, you would get in the region of 10 to the power of 23 free electrons per cubic centimeter. So you're talking orders of magnitude different. So actually, these intrinsic semiconductors are not that useful for practical purposes. I had to introduce them so that you can understand how they work, but actually we need to manipulate our semiconductors in reality to get them to work in our applications. And we do that by doing something called doping. You've probably heard of doping before. So doping, when you usually talk about it, is in terms of perhaps a sports person, an athlete who uses illicit substances to enhance their performance. And doping in this case is similar because what you're doing is adding something impure into a material in order to enhance performance. And the way that you do that is by adding or substituting impurities into our lattice. So here we have silicon again, and what we mean this time, we're not making a compound, it's not a 50-50 mix between different elements, but we're actually adding impurities. So where silicon is, we add perhaps a phosphorus atom in place of a silicon atom, and these are in very, very, very tiny quantities, right? You can see the low percentage here. These very small this very small amount of impurity atoms can make a huge difference to the conductivity, even though they're added in very small amounts. So they directly substitute in place of a silicon atom. And what happens here? Well, we know phosphorus, for example, is in group 5 of the periodic table. So the group 5 elements have 5 electrons in their outer shells. So that means that when phosphorus sits in the place of a silicon atom like you've got here, it has one extra electron that kind of it's not needed in bonding. So it's a very loosely bound into that outer orbital, but it's not required for covalent bonding. That electron is not actually shared with any of the other silicon atoms. And that means that if you add energy to the system, it takes very, very, very little energy for it to break free of its orbital because it's not involved in bonding. So that takes much less energy than to liberate one of the outer electrons from the silicon atom itself. So that one is now free in the material, and now if you apply a voltage or a potential difference, you can get current flow. So you add something from group 5 of the periodic table, and that's known, so this process is known as doping, and your phosphorus in this case is known as a dopant. And in this case, that dopant is known as a donor atom. And the reason why is because it donates an extra electron to the system. So you can see here the phosphorus, in this point, the extra electron is still in the outer orbital of the phosphorus. You add a little bit of energy and the phosphorus atom becomes ionized, right? Because that has a net positive charge because it's lost its electron that moves into the material that has the negative charge. So the material is always charge neutral, but in the case where you add something from group 5, you get an electron donated into the material, and the charge carriers, in this case, the extra charge carriers, are electrons which are negatively charged. So these materials are known as N-type doped materials. N for negative charges. So the material is not negative, the material is neutral, but the majority charge carriers, the extra charge carriers that you have here, are negative because they're electrons. The other thing that you can do with silicon is then take an atom from the other side of the periodic table. You take something from group 3. If you take something from group 3, for instance, boron only has 3 electrons in its outer shell, so it's actually missing an electron in order to be covalently bonded to the silicon atoms that are surrounding it. So that already has a hole, and it allows the electrons to very easily move into that hole. So it doesn't take a lot of energy for an electron that's already involved in covalent bonding to shift into that gap, into the hole, and then all of the electrons can start to move into the gap that's been left behind. So when boron is used in the system, or anything from group 3, it's known as it was also a dopant because it's the same doping process, but it's known as an acceptor atom. And the reason is because it's accepting an electron. It's accepting an electron into the hole, and again, it becomes positively ionized, and it becomes negatively ionized because it's accepted an electron, but your majority charge carriers in this case are holes which are positive. So these are known as p-type doped semiconductors, p-type, because the charge carriers, the majority charge carriers, are holes. Of course, if you keep on adding energy to the system and keep on adding, then all of a sudden you'll get back to the intrinsic situation, which is what we had before, where all of the other electrons will also be able to break free into the material. So there's the difference between your extrinsic situation, when you have a doped material, and an intrinsic situation, which is like the way that I was talking about before, where your electrons come straight from the conduction band, straight from the valence band into the conduction band. So you also need to know how temperature affects these extrinsic semiconductors. So once you have dopants in the situation, it's very different, okay? So there are 3 different regions that you need to know about. The first is at very low temperatures. So we're talking about under 100 degrees Kelvin. At very low temperatures, there isn't enough energy in the system at all in order to ionize the electrons from the dopant. Okay, so actually there's no conduction, and there are no charge carriers at a very, very low temperature. As temperature increases, if you have donor atoms, so if you've got phosphorus in your system, then it takes very little energy, very little heat in this case, in order to ionize those electrons and add them into the conduction band so that they can conduct electricity. And that's known as the extrinsic region because you've got conduction in an extrinsic type of semiconductor. Now, as the temperature gets higher and higher, it'll eventually start to thermally excite electrons from the valence band into the conduction band, and it just acts like a normal intrinsic semiconductor. So you end up with 3 different regions if you plot this on a graph: a freeze-out region, an extrinsic region, and an intrinsic region, and that looks like this. So you can see down one side, you've got the carrier concentration. So that's the number of charge carriers that you have per unit volume versus temperature across the x-axis. And you can see that at first, very little is happening until there's enough energy in the system that you get ionization. And then eventually it starts to get the electron-hole pairs like an intrinsic semiconductor. Of course, conductivity versus temperature is going to look very similar, because we've already said conductivity is proportional to the number of carriers, or the carrier concentration. So the shape actually looks the same, but what this is showing, you've still got your 3 regions, you've still got your freeze-out, your extrinsic, and your intrinsic. But what you also have here, this shows that the more doping you have, the more charge carriers you have in the extrinsic region, so the conductivity is also higher. So that's all that is showing.